Hello and good day, pre-algebra. Here with you to go over math packet number 9. I forgot to write this on here before I scan it in, but it is due March 25th. March 25th, it's about 2.5 weeks to finish this one up. First question here. A dance company held auditions to fill 3 spots in the company. After the first round, 2/3 of the dancers were cut. After the second round, only a quarter of the remaining dancers made it to the third round. 2 were cut after the third round, leaving 3 moving on to the fourth round. How many dancers attended the auditions? So if our ultimate goal here is to calculate how many dancers attended the auditions, we're going to label that as our variable. This N represents our whole group of dancers that showed up to try out here. And it says in round 1, or after the first round, 2/3 of the dancers were cut. So this whole group of dancers can be divided into 2 groups. 2/3 and what remains, which is 1/3. Okay, and really, since we're talking about a group of dancers that we've labeled N, we should say this is 2/3 of N and 2/3 of N, right? If N is 9, 2/3 of N is 6, 1/3 of 9 is 3. That means that 6 were cut and 3 get to move on, right? So 2/3 of our whole. Since 2/3 were cut, we can eliminate them. They are out of it. It says after the second round, only a fourth of the remaining dancers made it to the third round. A fourth of the remaining dancers. So we can split this group up into 3/4 and 1/4. But here's where the wording of this really comes into play, and we have to be careful. It says only a fourth of the remaining dancers. So when we write a fourth there, we're not talking about a fourth of the overall group of our original N. We're talking about a fourth of the third that moved on after the first round. And that word of, meaning that we're multiplying here, a fourth of a third is 1/12. So instead of 1/4, I'm going to put 1/12 here, saying that 1/12 of our original group moved on after round 2. A 12th of the original group. Okay? And then this group, this 1/12 of N, 2 were cut after the third round, leaving 3 to move on to the fourth round. So this now, we're not talking about fractions anymore. We're talking about actual dancers. 2 were cut and 3 got to move on. Okay? And so where I left you in class was, how many dancers were in that group? How many dancers made it past round 2? And we added these 2 together and we said 5, right? Because those 5 dancers, 2 were cut and 3 got to move on. So if 5 represents a 12th of the whole, or a 12th of the original group of dancers, what's that going to be? Okay, so that's where we left off in class, and you can pick it up from here. Next page. Andy is going to take a 30-question test in which he earns 9 points for every correct answer, loses 5 points for every wrong answer, and loses 1 point for every question he doesn't answer. Is it possible for Andy to earn a score of 0 on the test, and if so, how? And I mentioned that the every year I get 3 or 4 kids that turn in a packet saying Andy doesn't answer anything. Because usually on a test, if you don't answer anything, you will get a 0 on it. However, this particular test, he loses 1 point for every question he doesn't answer. So on a 30-question test, if Andy doesn't answer everything, then he's going to get a score of -30. So what you're really looking for here is recognizing that earning 9 points is like a positive 9. That's 9 points in your favor. Losing 5 points is like a -5. Your score drops by 5. And losing 1 point is like a -1. Your score drops by 1. So how can you arrange the numbers +9, -5, and -1 in a 30-question test to 0? Is it possible to do that? And how is it done? Okay. Next page is the 5-card challenge. Not much explanation needed here, I don't think. You are making a 1, and we did talk about in class how The easiest way to make a one, I think I gave this to you also, is anything divided by itself. So a 4-point freebie here, 6 plus 9 divided by 7 plus 8 will give us 15 divided by 15, which equals 1 whole, or 1. Okay, so there's a 4-point freebie for you. If you can find any other ways to divide something by itself, that would be handy. Next page, the area of the shaded region. Our goal here is to find the area of the entire figure as well as the shaded region. And the game plan that we came up with, first of all, knowing that the radius of these two half circles is 6, we were able to come up with the side length of the entire square. Knowing that a radius is from the center of the circle to the edge, we figured that this side would also be 6, making the whole side of the square 12. So the area of the overall figure, which is the area of the square, we found that fairly easily. To find the shaded region, though, we again find ourselves in a situation where we're going to have to take the area of the whole and subtract the unshaded region. Because there's really not a handy formula to find a shape like this and like this, right? So instead of finding the shaded area directly, let's subtract what we don't want, that white section, and we'll be left with what we do want, which is the shaded section. And the white section being 2 half circles, which is also 1 full circle, the area of a circle being pi times the radius squared. Basically, our game plan was, let's take the area of the square, and not equals, and subtract the area of a circle with a radius of 6. So if we start with the whole thing and take away what we don't want, we're left with what we do want, which is the shaded region. Next page, our pattern block page. Again, dealing with squares. Boy, I must like squares a lot. It's not so much that I love squares as I do the patterns that they present to us, particularly with perfect squares. And if you take a look at the green blocks here as you go from figure 1 to 2 to 3 to 4, figure 1 has 1 green block. Figure 2 has 4 of them. Figure 3 has 9 of them. And figure 4 has 16 of them. And what we remembered about the numbers 1, 4, 9, and 16, they're all perfect squares, right? And furthermore, actually, if you square the figure number, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, we can get there relatively easily. Then we looked at the total blocks section, and we noticed that, hey, this first figure is a 3 by 3 square. That's a total of 9. Our second figure is a 6 by 6 square. That's a total of 36. Then we have a 9 by 9 square, which is a total of 81. And we have a 12 by 12 square, which is a total of 144. And so we said, okay, so what would the total be in figure 5? And if you look at just the numbers, 9, 36, 81, 144, maybe not quite as obvious as looking at the side lengths of the square. 3, 6, 9, 12. The next figure is probably, following the pattern, going to have a side length of 15. And since it's a square, 15 times 15 would be 225. Okay? So perfect square patterns all throughout here to help us fill out this table. And then getting the purple blocks is simply, once we got 2 of the columns filled out, we can get that middle column with subtraction. 1 green block out of 9 total, that means there has to be 8 purple. 4 green blocks out of 36 total, there has to be 32 purple ones, right? 9 green blocks, 81 total, there has to be 72 purple ones, and so on and so forth. So lots of patterns here to work with, dealing with squares, and your job pre-algebra is to complete the table. Then we went to surface area of this rectangular prism. And we talked about how a lot of algebra is using what we know to find what we don't know. And so we look at this rectangular prism and we know the height's 5. We know it has a width of 9, but that base, this x value, is an unknown. If we're given the volume, how can we calculate that missing side length? We said, well, what do we know? We know the volume of a rectangular prism is base times width times height. We know the volume, because we're told, is 360. The base we don't know. The width is 9, and the height is 5. So we multiplied 9 and 5 together. We divided both sides by 45. And we get a value of 8. So this unknown side length of this rectangular prism is 8. And with that 8, we can answer the rest of the question, what is the surface area? And I'm also asking you to draw a net here, which you've drawn a net of a rectangular prism before, in packet number 1 or 2, actually. And what a net helps us do is it helps us see, what surfaces do we have here? How many surfaces are there, and what are their side lengths? So imagine this being like an Amazon box that we're going to lay out flat. So we have the bottom of the box. Okay, it's kind of our largest side there, largest face. And this has a base length of 8 and a width of 9, just going off of the values that we have there. Then comes the right side of our prism, and that's going to have a 5 and a 9. Then imagine folding over the top of that box, so it's lying flat on a flat surface. The top comes next, and that's the same size as the bottom, so that will have an 8 and a 9 there. And then the left side of our prism, you can put that on either end of our net here, but it might help visualize things for you better if we connect it to our bottom, which is going to have 5 and 9 here. Okay, so we have our bottom. Oh, you can't see me point on this. So this represents the bottom of the box. This is the right face of it. This is the top of the box, and this is the left face of it. So the only two faces that we're missing are the front and the back. And the front and the back are going to connect to either the top or the bottom, doesn't matter which one. But this is going to be the front, and this is going to be the back. This will have a length of 8 and a width of 5. Okay, so there's our net of this figure here. And what I'm asking you to do is now find the surface area, which is the sum of all of the areas of the faces. So you're just going to go through these 6 faces and calculate the area of each of them and add them all up. 8 times 9, that's an area of 72, and so on and so forth. And the surface area is the sum of all of them. Next page, we bring back the magnificent 7, the 7 solids that we talked about earlier this year in packets 1 through 7. Same idea as what you had to do in packet number 8. I've changed what the volume is for each of them, but given that volume, you are to write the formula for 3 of the 7 shapes that you'd like to do, and then what are possible length, width, and height values, or if you're doing some on the bottom here, radius and height values, that would get you to that given volume. So if the volume of this rectangular prism is 60, the formula is base times width times height. I'm essentially looking for 3 values that multiply to make 60, okay, as possible length, width, and height values. And in pre-algebra, you need to do 3 of these 7 shapes. Next one is Fibonacci and the golden ratio. We didn't get to talk about this one in class, but the golden ratio is naturally pleasing to the eye. And everything from shapes to nature, to human faces, the closer an object is to the golden ratio, the more it resonates with beauty. To many, it is the gateway by which God shows himself in creation. Consider a segment that is divided into two parts, A and B. I've got that here. Okay, here's our segment, right? And it's divided into two parts, A and B. If the ratio of the whole segment, which is A and B together, to the long section A is equal to the ratio of the long section to the short section, the segment has been divided in the golden ratio. Below is a model. So we're talking about rates and ratios now. What this is saying is that if the whole segment compared to segment or part A is equal to part A divided by part B, it's said to be in the golden ratio. If you're having a difficult time grasping this, it's okay. It's something that has been extensively researched for centuries, and for as much as mathematicians have learned about it, there's still much that remains a mystery. How does this apply to Fibonacci? The beginning of the Fibonacci sequence is below, and as consecutive elements are divided, larger divided by smaller, the quotient approaches the golden ratio. See for yourself by writing the quotients below, round each quotient to the nearest 10,000th. Okay, and the nearest 10,000th. So as we go through the Fibonacci sequence here, 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, 5 divided by 3. Here's the first time where you get to round to the nearest 10,000th. If you divide 5 by 3 in your calculator, you get 1.66 repeating, right? The nearest 10,000th, think back to your place values here, tenths, hundredths, thousandths, 10,000ths. Okay, so 4 places after the decimal point, 1.6667. And you're going to go through each of these quotients, and as you're noticing here, we're just dividing. Our first one is 1 divided by 1, then 2 divided by 1, then 3 divided by 2, 5 divided by 3, and so on and so forth. We're dividing these elements of the Fibonacci sequence, and you're going to notice that you're going to approach a specific number. That number that you approach, that your quotient gets closer and closer to, is the golden ratio. And we'll talk more about what that golden ratio means. I've got a YouTube video to show you on it, just basically why that is such an important or mysterious ratio in mathematics, nature, art, music, etc. So there is your math exploration for packet 9. Then we go on to mean, median, and mode. Pre-algebra. At the grocery store, you buy 3 oranges for $1.20 each, 2 bananas for 99 cents each, 4 tomatoes for 75 cents each, and 3 loaves of bread for $2.50 each. Find the mean, median, and the mode of prices for each item purchased. And just as a reminder here, so you don't miss one, there are 12 items. So list all 12 prices and find the mean, the median, and the mode of those 12. You don't need to fill anything out here. That's more for algebra and geometry. Lastly, our polyomino question. Hey, nice to see you. Where in this figure do those 8 polyominoes fit in? Just a reminder, they can't be turned or rotated or anything like that. So this one, you can really use clues to help you place these. There are only a certain number of spots that, for example, this one here can go. It's pretty much either in the H or the Y, right? And this one, this long fiver here, there's only a certain number of places where that can go. So this one, more so than any others, can really use those clues to help you place these polyominoes. But there you go. That is math packet number 9. It is due on March 25th. Make sure you turn it in early so I can check it over, give us some pointers on it. That's how you math. Don't forget to like and subscribe, and have a great day.